Hello everybody, this lesson is going to look at how the number of particles in a solution can affect different properties. We call those types of properties colligative properties. So colligative properties are ones in which the value depends on the number of particles present, not on what type of particles are present, which is kind of a strange idea. So what we're going to be looking at is if you dump a salt into water, for example, how many ions does it break apart into? Or does it stay one particle, something like sugar, that does not dissociate, right? Those are the things we're going to be looking at in this lesson. The reason we end up with a difference between the pure substance and the solution for things like boiling point, vapor pressure lowering, things like that, is because there are going to be different forces present, and we end up with solute particles taking the place of where solvent would be at the surface. So things are not allowed to vaporize as much because there's not as many places for them to do that, because the solute is kind of taking up space, it's in the way. So the ones that we'll be talking about are boiling point elevation. How much higher does it boil at? Freezing point depression. It will freeze at a lower temperature. And then something that you probably learned about in biology called osmotic pressure. If you don't remember what that is, I'll show you some pictures at the end that will probably jog your memory. So when we're doing these colligative properties, we have to take into account the number of particles things dissociate into. So you can see here some examples. In the first one, AB breaks apart into two separate ions. C2D breaks apart into three separate ions. Something like this is a non-electrolyte, something like sugar, right? That does not break apart. It dissolves. It gets mixed in, but it's not going to dissociate. The number of particles that it dissociates into is called the Van Hoff factor. We use a lowercase I. So the Van Hoff factor here would be 2, this one would be 3, and this one would be 1. This substance will have twice the effect as this one down here. Over here, this would have 3 times the effect as the one down here. We will have to take that into account when we do our calculations. Why don't you look at these examples, pause the video, and try to write down next to each equation what the Van Hoff factor would be. All right, let's see how it went. Here, broke into 2, so I equals 2. Same thing here. You have to remember that your polyatomic ions stay as a little packaged unit. So NO3- is only one particle. The next one, I equals 3, we get 1 magnesium, but we get 2 chlorides. This one is 3 as well. 2 sodiums and 1 sulfate. And then at the bottom, this would break into 4. Now, in real life, the Van Hoff factor, just like everything we do, is a simplification, right? It's pretending everything is ideal and perfect. And in real life, the Van Hoff factor only really works if your solution is very dilute. The more concentrated it gets, the less perfect it is. So you can see in this chart, if you had a perfect dilute solution, everything was ideal on the right hand side, yes, your Van Hoff factor for sodium chloride would be 2. But the more concentrated you get, the less ideal your number gets. Your Van Hoff factor, your real factor, gets smaller because not all the salt's going to dissociate. Just because you dump it in water doesn't mean 100% is going to dissociate. So The more concentrated it gets, the less perfect your answer would be. Everything we're doing, unless they give you the real Van 't Hoff factor, you just assume it's ideal. But if they told you, hey, the real factor is 1.81, then in your calculations use it. If they don't tell you, then you would just use 2. So calculating the freezing point depression uses the Van 't Hoff factor. For each substance, there would be a unique K value. This is the amount that it's depressed kilogram per mole. So you would need to be told this, or maybe you would be looking for that number. I is your Van 't Hoff factor, and you'll see here we're using molality. So be careful about that, not concentration like we normally do, molarity. This time we're using molality. There's a lot of real-life examples that use this idea of colligative properties. You put antifreeze in your car so that all the fluids won't freeze when it's cold outside. The antifreeze makes it so that all the fluids in your car would freeze at a lower temperature. On a phase diagram, you can see that it shifts where those lines are. So going from a solid to a liquid, right, if you're trying to freeze it, that red line is now at a lower temperature. So you can see here, it's almost the same equation for boiling point elevation, but we would be using a different K value, the one specific to boiling for this substance. We're still using molality. You would get these numbers provided to you in a chart, or worst case, look them up online. These are not things you'd be expected to memorize. All right, let's look at osmotic pressure. If you set up a tube like this, and you have this special membrane, the membrane allows solvent to get through, but the solute can't get through it. So it's like a one-way membrane. The blue over here is pure solvent, and over here is a solution where you have your solute particles mixed in. If you were to just let this sit, the solvent would start going into the solution side, trying to dilute it. It doesn't like that there's a difference here in concentrations. It's trying to come over here and dilute it to make them closer to equal concentrations. If, however, you apply a pressure on this side to cram this solution down, you can counterbalance the pressure of the solvent trying to get into the solution side. So sometimes maybe you only have to apply a little bit, or maybe you have to apply a lot. The amount of pressure you have to apply to prevent the solvent from coming through that membrane is called the osmotic pressure. And in biology, there's lots of applications of this. We only really care about this because it's one of those colligative properties we're trying to understand. So if you want to calculate the pressure, you would use this equation here. And this time you see it's a capital M, we are using the molarity. R is our ideal gas constant. Depending, remember, on what unit of pressure we're interested in, you may change this. If you want torr, it would be a different number, for example. And then we use kelvins for our temperature. So you can see here, on the right, this is less concentrated than the left. So water will try to get through this side. And the water line would go up. if you want to apply pressure here to cram it back to the other side, that would be the osmotic pressure. One quick thing that sometimes comes up is that not all liquids you see are solutions. Some are called suspensions and some are called colloids. So suspensions are when the particles are so big that if you were to just let it sit there on the table, they would fall to the bottom. They cannot stay mixed in. They're too big. Colloids are strange things because they're an in-between. They're not considered small enough to be a solution. They're not considered big enough to be a suspension. They're this in-between. And colloids have really interesting properties. And there's a lot of everyday real-life things that are colloids that you probably didn't realize. Things like fog, smoke, whipped cream. Milk is the most common example. So you can see here a lot of things that you might think of as liquids like milk or even solids like butter are actually this strange type of not really a solution. They're called a colloid. One of the interesting things about colloids is that they cause light to scatter because the light is essentially bouncing off of the particles. In a solution, the particles are so small that the light just goes right through. You can't see it. So if you use a little laser pointer and you shoot it through some salt water, you won't see the beam inside the solution. But if you put it through something else that was a colloid, you would be able to see the beam inside. So you can see here, this one's the solution and this one's the colloid. So the rest of this presentation is going to be practice problems. I have one diagram to show you that I think is helpful for these practice problems because if you're like me, sometimes you lose track of, wait, which equation uses molarity, which one uses molality, which property goes with which. So I found this diagram where it kind of shows you, well, here for these two things, you got to use the molality. But for vapor pressure, you would use mole fraction. For osmotic pressure, you would use molarity. This is kind of showing you a little roadmap of how you can get to things. You could go from molality to mole fractions. You could convert from molality to molarity. So maybe this will be helpful to you. So let's do some practice problems. Remember, pause the video to give yourself time. Which one of those is not a colligative property? Density elevation, that's not a thing, right? The rest are. All right, a calculation. This time we want to see what the vapor pressure would be if you dumped some salt into the water. And they tried to give you a hint in parentheses. They tried to remind you that salt is going to break apart into different ions. So when you do your Raoult's law, when you're calculating your moles of solute, you're going to have to be careful because you're going to need to calculate the moles of solute particles. And sodium chloride breaks into 2 particles. So when you're doing your dimensional analysis, take that into account. So pause the video and give it a try. All right, let's see how it went. How'd you do? We started with our grams of salt, convert to moles, and now this is where Van Hoff comes in, because 1 mole of sodium chloride will dissociate into 2 moles of ions. So when you're trying to find your solute, you really have 4.15 moles of solute. So now let's do our solvent. We have 100 grams of solvent, molar mass of water. Now we know how many moles of solvent we have. Time for mole fraction. Water over the solution. And now, remember our Raoult's law, we can take the mole fraction, multiply it by what the pure vapor pressure would be, and we now know that it's a little bit lower, isn't it? If you forgot to take into account salt breaks apart into two ions, you would have gotten 22.9. It would have been lower, but not as much as if you had remembered it was two ions. All right, let's try another one. So they're telling you that your mixture, your solution, will have twice as many moles of heptane as octane. They don't tell you how many though, do they? So make your life easy. Let's pretend octane has 1 mole and heptane has 2 moles. Pause the video and see if you can do this one. All right. So I'm going to make my life easy and I'm going to pick nice simple numbers. The reason I can do that is that this calculation is not about the specific number of moles, is it? It's about the mole fraction. If I had said 2 and 4, that's the same mole fraction. If I had said 100 and 200, it's the same mole fraction. If I had said 1.5 and 3, right? It's always going to be the same fraction. That's one of the nice things about fractions. So I have 1 mole of octane and there's 3 moles total present. I'm going to have the pressure of the pure octane. Then I have 2 moles of heptane over 3 moles total. And I have the pressure of the pure heptane. So I can find out that this solution would have that pressure. And you can see it's between our two pressures, isn't it? It's somewhere between 92 and 31. But since I have more heptane, it's closer to the heptane value, isn't it? All right, a new one. So this time we're going to do boiling point change. So we're looking for a delta T. They gave you your KB. You didn't have to look it up or anything. And if you notice in parentheses, they tell you it's a non-volatile, non-ionizing compound. The non-ionizing part's telling you what your I value is. It is not going to break apart into ions. So pause this one, give it a try. Remember, you're going to use molality this time. All right. It's going to boil 6.89 degrees higher than normal. So we have our moles over kilograms of solvent. Remember, they will often give you it in grams and you have to convert. Since it was non-ionizing, my Hoff Factor, my I value is a 1. It tells me that this is how much higher the boiling point will be for every molality there is. And I have this many molalities. So I find out it's going to boil about 6 degrees hotter. Often people will ask, oh, this is why you add salt to water when you're boiling pasta, to make it boil at a higher temperature. The problem with that is you'd have to add so much salt. You have to add like a pound of salt in your pot before you would get a 1 degree temp change. So, that is more about flavoring the pasta. It doesn't really make it cook any faster, even though that's kind of a myth people have. But if you put that much salt in your water, that'd be a little crazy. All right, this time we're looking at freezing point. But it's a little bit more complicated because we're not asking for what the freezing point depression is. They told us that info. They want the molar mass. But molar mass does not show up in our equation, does it? You need to stop and write down the units for molar mass and ask yourself, how can I use this information to get grams per mole? They gave me grams. I got 7.12 grams. So I need to somehow use this freezing point calculation to solve for moles of solute. Pause the video, see if you can set it up. Get to the point where you can divide 7.12 by the number of moles that is. All right, the molar mass of this unknown substance is 143 grams per mole. So let's see how we got there. We are going to use our delta T equation. I know that it's going to freeze 1.02 degrees lower than normal. It didn't tell me how many particles it breaks into, so that means I can assume it doesn't. I can assume it's going to just be a 1 for my I value. They gave me K, and I don't know the molality. So I'm solving for molality, and I find out when you solve for M, you get 0.199. And this is where you should write down what your units are, because molality means moles of solute per kilogram of solvent. But I don't have a kilogram of solvent, do I? I have 0.25 kilograms. So I can set this up to say this molality is X number of moles of solute over 0.25 kilograms of solvent. And that tells me that in order to have gotten a 1.02 degree depression of my freezing point, I had to add this many moles to this many kilograms. Well, now I want molar mass, right? 7.12 grams was this many moles. So I end up with my molar mass of 143. I find it so amazing that they can do such a simple experiment and figure out what a molar mass of a molecule that is too small to be seen is. You see what temperature a pure solvent freezes at, you dump something into it, you freeze the solution, and you see what a difference in temp that is. And it tells you something about that solute. And that's a really simple experiment, isn't it? And we're able to do that because we understand units. Okay, one last one. Let's do an osmotic pressure one. You pause the video and try to calculate how much pressure you would have to apply to stop that osmosis from occurring. All right, how'd you do? Since it's molarity, we're going to have to get moles per liter. So let's do grams to moles. They told me how much solution I had. So to get my molarity, it's moles per liter. Make sure you convert your milliliters. My hydrocarbon is not going to break into ions, right? So my Hoff Factor is a 1. I have my molarity. It wants it in torr, so R is going to be 62.4, and I'm going to convert my Celsius into Kelvin. One of the things I really like about colligative properties and all of these different calculations is I feel like it takes so many things you learned in honors chem and puts them all together. And that you have to be so comfortable with the baby steps that you don't have to waste time or thought on them. Do you remember in honors chem when we practiced over and over and over converting grams to moles? And now it has to be second nature. And when we learned how to do King Henry conversions to go from milliliters to liters, and converting Celsius to kelvins, picking R values, knowing if something's ionic or covalent, these are all baby steps that you worked at in honors chem. And now we just do them like no big deal because that's not the main point of the problems anymore. The main point of the problems is to go 10 steps further now. If you had me for honors chem, you remember I always said, you can't take 5 minutes to convert from grams to moles. You can't take 5 minutes to find a molar mass or you'll never finish. And I think that these colligative properties really emphasize all those baby steps. All right, everybody, that was it. I hope this was helpful. Bye.